Hey everyone, and welcome to The Explainer. Today, we're diving straight into a really fascinating journey to uncover the hidden chemistry behind one of the most transformative tech breakthroughs of our era, additive manufacturing. Now, we usually think of 3D printing as this purely mechanical or digital marvel, right? A victory of clever software and robotics. But the truth is, the real magic, and honestly the real frustration, is actually happening way down at the molecular level. So, let me ask you something. What do you think is the absolute biggest bottleneck in 3D printing today? When you look at a high-end printer, you might guess it's the resolution of the 3D models, or the precision of the laser, or maybe even the motor speeds. But it's actually none of those. The mechanics of these machines are already nearly flawless. The real bottleneck? It's the material itself. Okay, let's dive into this. The hardware of an SLA, or stereolithography printer, is literally mesmerizing to watch. You have this platform dipping into a vat of liquid, a laser firing from below, and an object just being pulled right out of the liquid, layer by layer. The engineering is brilliant. But that vat of liquid resin? Yeah, that's where the headaches begin. To see how scientists are tackling this, here is our roadmap for today. We'll cover the SLA bottleneck, the chemical recipe, testing the perfect mix, the winning formula, and finally, the high-tech industry impact. Let's get right to it.
All right, Section 1, the SLA 3D printing bottleneck.
Now, you're likely familiar with SLA. On a basic level, it's a rapid prototyping tech where a liquid, photosensitive resin solidifies the exact microsecond it gets hit by a specific UV light laser. When it works, it is stunning. We're talking printing accuracy down to an incredible 20 micrometers, way better than most other fabrication methods out there. But that raw liquid resin, it can be a total nightmare. It often has super high viscosity, meaning it's just too thick to flow smoothly. It can have weak mechanical strength, giving you brittle prints. And the absolute worst offender is volumetric shrinkage. That's when your final solid object warps and literally ends up a totally different size than the digital file you sent to the printer.
Moving on to Section 2, the chemical recipe.
Think of engineering a brand new resin like following a highly complex, really high-stakes baking recipe. For our ingredients, our structural base, let's call it our flour, is an epoxy acrylate named BAEA. To keep that base from turning into sludge, we add reactive diluents, HDDA and TPGDA. Those act like the water, keeping everything flowing beautifully. Then we have PETA, a cross-linking agent that acts like the yeast, tying the whole molecular structure together for strength. Finally, the photoinitiators, 1173 and TPO, act as the UV heat triggers. Oh, and get this, researchers actually found that mixing both of these initiators together creates a synergistic effect that stops oxygen in the air from ruining the print. It's an incredibly delicate, highly reactive cocktail.
And what's really interesting here is that we don't have to just guess about this chemistry. Using real-time FTIR spectroscopy, we can mathematically watch the UV laser do its job. Seeing those peaks drop over time is the literal real-time visualization of invisible carbon double bonds snapping apart and forming single bonds. It is exactly what solidifies the liquid layer by layer in a matter of seconds.
Which brings us to Section 3, testing the perfect mix. Knowing the ingredients is just step 1. Finding the exact ratios, that's where the real science happens. The researchers were immediately hit with this massive trade-off tension. If you add more of those fluid diluents, the resin flows perfectly, which the printer absolutely loves. But that excess fluidity ruins the physical strength of the cross-link network, making the object snap easily. Even worse, it makes the final object shrink in size as it cures. So you fix one problem, and you completely ruin two others.
Now, you might be wondering, hey, why not just heat the resin up? Because simply heating the resin dramatically lowers its viscosity. It flows like water. But there is a massive catch here. Heating the vat risks thermal curing. That means the resin might actually start hardening before the printing even starts, completely destroying its shelf life. So the scientists realized they had to tweak the molecular polarity of the diluents themselves, specifically relying on TPGDA, to keep the resin perfectly fluid right at a standard room temperature of 25 degrees Celsius.
Balancing strength and accuracy became this insane tightrope walk. The push and pull in the experimental data is wild. Add too much PETA crosslinker and the object shrinks uncontrollably. Add too much BAA base and the resin gets way too thick to even print. The experimental process required testing dozens of precise molar variations just to find a mathematical sweet spot where the liquid wouldn't warp, wouldn't break, and wouldn't clog the machine.
Okay, Section 4, the winning formula.
Out of all that trial and error, the researchers finally discovered the optimal chemical combination, which they dubbed the B2 mixture. And it delivered two huge victories. First up, 239.53 millipascal seconds, the B2 formula achieved this incredibly low, absolutely perfect viscosity at 25 degrees Celsius. This meant the printer's mechanical arm could just glide through the vat smoothly, without fighting a thick, sticky goop, which dramatically speeds up the whole printing process.
And here is the second major victory, 4.36%. That is a staggeringly low minimum shrinkage rate. In the world of additive manufacturing, this is huge. It means that when the resin cures from a liquid to a solid, it stays almost perfectly true to size. The physical object pulled out of the vat actually matches the digital CAD design without any severe warping or distortion.
This brilliantly illustrates exactly why the B2 formula is such a game changer. When you compare B2 to other experimental resins recently reported in the scientific literature, the difference is night and day. Other resins either had terrible shrinkage, or they were super brittle, or they were way too thick. B2 achieves the ultimate Goldilocks balance. It hits high tensile strength, ideal fluid flow, and dimensional accuracy, all at the same time.
But, data on a chart is one thing. Seeing it in reality is another. Take a look at the visual proof of the B2 formula in action. They used it to print an intricate Voronoi ball and a delicate nanotube structure. Under a microscope, you can literally see the stunning accuracy. Distinct, perfectly stacked print layers separated by just 50 micrometers. No clogging, no warping, just perfect structural integrity.
Finally, Section 5, High-Tech Industry Impact. Let's zoom out for a second. Why does tweaking invisible molecules in a lab actually matter to us on a macro level? Well, because unlocking this kind of zero shrinkage, high-strength accuracy transforms entire industries. Think about biomedicine. Printing a custom medical device or implant requires life-or-death accuracy. A 4% shrinkage versus a 10% shrinkage changes the entire fit of an implant. In microelectronics, components are shrinking down to microscopic levels where there's literally zero margin for error. Automotive engineers need rapid prototypes that can withstand real-world mechanical stress testing without shattering. This highly specialized chemistry is exactly what makes those next-gen advancements possible.
We've seen how perfectly balancing invisible molecules, tweaking reactive diluents, and optimizing photoinitiators can completely remove the physical bottlenecks of manufacturing. So I'll need you with this to think about. As chemistry continues to catch up with our digital imaginations, and if the structural materials in our printers soon have absolutely zero limitations, what would you print next? Thanks for joining me on this explainer, and I'll catch you next time.